displacement, velocity, and acceleration against time for an object moving in a straight line. The time axis is shown to the same scale on all three graphs. So which graph represents which quantity of acceleration, displacement, and velocity here? Well, a relationship we know is that v equals ds by dt, and then we know acceleration equals dv by dt. So in order to really answer this question, we need to look at the derivatives of one graph and how that might possibly give us another one. Now that seems like quite a hard task, so we need to look for a derivative that we really know. And so a good point to start would be a stationary point of any of these. So for example, if we look at P, it has a stationary point here. So its derivative should have a 0 at that coordinate. So if you look, R could be the derivative of P. So that's a possible one. Okay, now let's look at Q. Q would also have a derivative of 0 around here. And so it could also match up there. That's strange. So R could also be maybe dq by dt, just going off this so far. Now R, if you look at its stationary points, has one here and here. So its derivative would have 2 zeros. Is there anywhere that this matches up? Well, actually, this matches up with Q. So what do we know here? We know that the derivative of R should be Q. So actually, dr by dt equals Q. So Q has to be velocity or acceleration. So it cannot be a displacement term. So this one has Q as displacement. Should probably actually rub that out. And then Q could not be displacement from this one. And then we said R could possibly be the derivative of P. So if we look at this, we have that P has a negative gradient to begin with, so that makes sense. And then possibly a straight line region where its derivative would be the lowest, or like the maximum negative term. It then has a derivative of 0 here that we said matched up with this term. And then the derivative after that is positive, so it carries on, goes to a point of inflection possibly, or maximum positive gradient, I should say, and then gets less and less positive afterwards. So it seems reasonable here that R equals dp by dt. So that means R could also not be a displacement term. So we'd expect P to be the displacement term here. So we could either have this or this. And so we have R is a derivative of displacement. So R should be the velocity. And then Q should be acceleration. So our answer is C. Now, this question's a bit ambiguous. So you might want to just look at how you could have come up with which graph is a derivative of which. So you're mainly looking here for either stationary points or certain values that you could look at. So we firstly got that dr by dt was Q. So Q is the gradient of R. So we just needed to relate P to either Q or R. And we knew Q would not be the derivative of P because Q is negative at the start and carries on being negative for a while and should carry on being negative, but the gradient of P is negative until this point. So I should mark this up here. So, and then it still carries on being negative past that point, whereas Q does not obey that. So we knew Q could not be the derivative of P, but Q was the derivative of R. Could P possibly be the derivative of Q? So if we differentiate this, we get positive, 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 and then we get positive, positive, positive here. So P could not be the derivative of Q either. So this is just a good way to check whether any of the other possibilities might have worked, might not have worked, but we can be pretty convinced that graph P is a displacement, graph Q is acceleration, and graph R is the velocity.